Section 14.3 is one-side limits and continuity. I would pause the video and write down these notes. So far everything we've talked about is as you approach from both sides of an x-coordinate. Now we're going to talk about one-side limits, so we're only approaching from one side. So a left-hand limit we denote with a little negative sign up here in the right corner, which means as x approaches c, but is still smaller than c. So if you look at it on a graph as it's approaching from the left, then your y-coordinates are approaching some value L. Right-hand limits we denote with a little plus sign in the upper right-hand corner, which means as you approach c, but from the left, or excuse me, from the right, so you're still bigger than c, then your function approaches some value r. A limit exists, the limit as x approaches c of f of x exists if and only if your two left and right hand limits are equal to each other. So if it's approaching the same thing from the left and the right. One-side limits are especially helpful when you have piecewise functions. So here we have a piecewise function where the split value is 2. So first thing we want to do is we want to find the limit as x approaches 2 from the left, which means we want to approach 2 but still be smaller than 2. So what section of this piecewise function would we use if we want to be smaller than 2? So right here that says you're approaching 2, but you're still staying smaller than 2. So when I take the left-hand limit, that's the side that I'm going to use. So I'm going to take the limit as x approaches 2 from the left of 2x minus 1. And just like we talked about in the previous section, if you can plug in the value, then you just plug in the x value. In here, there's no domain issues, so I'm just going to plug in 2, and I end up with 3. So as you approach the limit as you approach 2 from the left, you're going to get 3. So now pause the video and try the limit as x approaches 2 from the right. What part of the piecewise function are you going to use, and then what's the limit there? So we want to approach 2 but still be larger than 2, so we're going to take the part of the piecewise function where we're greater than 2. So that's the x minus 2. So I'm going to take the limit as x approaches 2 from the right of x minus 2. I can plug in 2, there's no domain issues, so you end up with 0. So then the last part says we want the limit as x approaches 2, just the regular limit of f of x. So we just had a theorem that said the limit exists if and only if the two one-sided limits are equal to each other. So does this limit exist, and if so, where is it? So the limit as x approaches 2 from the left was equal to 3, and the limit as x approaches 2 from the right was equal to 0. Those aren't equal to each other, so the limit as x approaches 2 of f of x does not exist. The next part is continuity. A continuous graph is unbroken. There's no holes, jumps, or gaps. If you can draw the entire graph without picking up your pencil, think of a sine graph or a parabola, that would be continuous. The way we prove continuity is first we prove that the function actually exists at that x value, so does it even have a y-coordinate there? The second thing we prove is that the limit exists there. So a lot of times you're going to have to use left and right hand limits to prove that this limit exists. And the third part is proving that those two are actually equal, because as we talked about in the previous sections, you can have a y-coordinate and you can have a limit, but they could be different values. If you know that two functions are continuous, then the sum, difference, product, and quotient, as long as the denominator is not equal to 0, are also continuous. When you go to prove continuity, you actually have to show all three of these steps. If at any point it fails, so for instance, if you do step 1 and the function doesn't actually exist there, you can just stop and say it's not continuous. But to prove that it is continuous, you have to prove all three of these are true. Discontinuity, a function that's not continuous, it can be discontinuous by failing any of the 3 steps that we use to prove continuity. There's 2 types of discontinuity. One is called removable. This is basically a hole. If you were to fill in that hole, you would make it continuous. That would be removable discontinuity. Anything else, asymptotes, jumps, gaps, those are all called non-removable. So we want to try to test to see if f of x is continuous at c. Our c value is equal to 2. So our first step when proving continuity is to prove that f of c, or in this case f of 2, exists, which means just finding the y-coordinate at x equals 2. So pause the video and go ahead and find if f of 2 exists, and if so, what that value is. So if you plug in 2, you end up with a -6. So the function does actually exist at f of 2. So step 1 is done. So now we move on to step 2. Step 2 is finding the limit as x approaches 2 of f of x. So sometimes you have to do left and right hand limits to prove this. If you just have a regular function where there's nothing funky going on at x equals 2, like we did in 13.2, then you can just evaluate that normally. So go ahead and pause the video and find the limit as x approaches 2 of f of x. So this is just a polynomial. There's nothing weird going on at x equals 2. There's no piecewise function. In fact, you can just plug in x equals 2 because it doesn't make a denominator 0 or anything. So if you plug in x equals 2, you end up with -6. So the limit does exist there. So now it's past step 1, it's past step 2. So now we move on to step 3. So step 3 asks, does the y-coordinate at 2 equal the limit at 2? F of 2 is equal to -6. And the limit as x approaches 2 of f of x was equal to -6. So these two are in fact equal to each other. So this passed all 3 steps, so therefore f of x is continuous at x equals +2. You can't say that it's continuous at every single point, just that it's continuous at this specific point. So once you pass all 3 steps, your final answer is yes, it is continuous. So now we have a piecewise function and we want to decide if f of x is continuous at x equals c, in this case c is equal to 1, which is this break point of our piecewise function. So step 1 again is to find f of c, so go ahead and pause the video and find f of c. So piecewise function, it says that at x equals 1, y equals 2, so f of 1 is equal to 2, which means it exists. So that means we move on to step number 2, which is finding the limit as x approaches 1. So for this function, because we have a piecewise function and the function is acting differently on either side of x equals 1, on x is less than 1, it's behaving like this function, x cubed minus 1 over x squared minus 1. And then for x is greater than 1, it's acting like this function 3 over x plus 1. This is the situation where we need to use right and left hand limits. So in order to find the actual limit as x approaches 1 of the function, we have to do the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. So if we want the limit as x approaches 1 from the left, which means that we are going to approach 1 but still be smaller than it, which part of the function are we going to use? So if we want to approach it but still be smaller than, we're going to use this part of the function, this top part. So go ahead and find the limit of that top part of the function. So if we use that top part of the function, you can't just plug in 1 because it'll make the denominator 0. So instead you factor the numerator and the denominator, and this x minus 1 factor cancels out. Once it cancels out, now you can plug in 1 and you end up with 3 over 2. So that's just the left-hand limit. Now we need to also find the right-hand limit. So if you want to use the right-hand limit, that means you want to approach 1 but still be larger than 1. So we're going to use which part of the function? We're going to use this bottom part of the function. So go ahead and pause the video and find the right-hand limit of this function. So on this one, the limit as x approaches 1 from the right of 3 over x plus 1. You can just plug in 1, it doesn't make the denominator 0, and you end up with 3 over 2. Because these are the same value, we know therefore that the limit does exist and the limit is 3/2. If those had been two different numbers, the limit wouldn't exist. You could stop after step 2. So we found the limit, it exists, we passed step 2. So now we move on to step 3, which is testing to see if f of 1 is equal to the limit as x approaches 1 of f of x. So go ahead and pause the video and test that and decide whether or not f of x is continuous at x equals 1. So f of 1 was equal to 2, and the limit as x approaches 1 of f of x was equal to 3/2. Those are not equal, so this fails step 3. The function is not continuous at x equals 1. So it passed step 1, the function existed. It passed step 2, the limit existed, but it fails step 3. Those two values are not the same. So whenever you're trying to prove continuity, you need to show all 3 of these steps. As soon as it fails 1, you can say it's discontinuous or not continuous at that value. But if you want to prove continuity, you have to prove all 3 of these.